Hello, everyone, and welcome to the show. I'm Max, and this is Into the Wild Blue Yonder, Episode 8 of PQ Adic Analysis and the Collatz Conjecture, the video series that, as I'm sure you all know, I am making to accompany my 2022 PhD dissertation of the same name. This is the final episode of my originally planned run, though more may follow if the need arises. So if you've made it this far, let me just say thank you and congratulations. You've climbed to the mountaintop, and so we can finally start talking about putting together all of the material we've covered so far. This episode is going to be a little bit schizophrenic, as it is an exposition of the main lines of my research as they currently stand. One of the reasons for the delay in this video is that almost all of this stuff is new, with the exception of the first section, which we'll cover momentarily. Everything I'm going to be presenting with you in this episode is stuff that it goes entirely beyond my dissertation, which I've been actively working on in the past 2 years since I graduated with my PhD. So we're going to start with the Tauberian spectral theorem, which was the big capstone of my dissertation that put together everything that I was doing so far. So, as I mentioned back in episode 2, I view my dissertation as a triptych. The first component of it is the Neumann itself, and alongside that, the correspondence principle. Together, these provide us a new formalism for studying Collatz-type problems, and it then gives us an object, the Neumann, to investigate, which we can attack using analysis and all of the algebraic techniques that come out of that. The second branch of my dissertation were my novel discoveries in PQ-adic analysis, such as quasi-integrability and my PQ-adic Wiener-Tauberian theorem. With these, I showed that a extremely exotic and obscure area of non-Archimedean analysis was, in fact, far richer horizon to study than was previously believed. The third and final innovation in my dissertation was using these two branches to, in tandem, to create a new method for approaching Collatz-type problems, and this occurs by a way of non-Archimedean Fourier analysis, and most of all, spectral theory. In the beginning of episode 2, I explained how these ideas of non-Archimedean spectral theory worked, but since that was quite a while ago, I think it's worth going over it one more time before we finally dive into the Tauberian spectral theorem and all of its consequences. So, by the correspondence principle, we know that the periodic points and divergent points of the shortened Qx plus 1 map TQ are controlled by the rational integer values that chi-q takes as its input varies over the two adic integers. For periodic points, this correspondence is both necessary and sufficient, whereas for divergent points, at the moment, we only know that the correspondence is sufficient, but I strongly suspect that it is also necessary. As we saw in our discussion of rising continuity in episode 7, given a frame f on the p-adic integers, the space C rise of f is the space of f rising continuous functions, and this is a locally convex topological ring. And on the other hand, the space of bounded rising continuous functions, C rise bounded, was a complete metrizable ring when we equip it with this ring norm thing. So in both cases, we obtained a topological ring structure using pointwise addition and pointwise multiplication of functions, and thus we can consider the units of these rings, which are those elements whose multiplicative inverses are also elements of the ring. The final piece of the puzzle comes from the observation that our rings are not just rings, but algebras, and in fact, topological algebras. For pedants, for us, all algebras will be associative and commutative, though not necessarily unital. So let's just recall what an algebra and a topological algebra are. Let K be a field. An algebra over K, also called a K-algebra, is a K vector space denoted A, equipped with a symmetric k bilinear map B, which we call multiplication. The bilinearity requirement here, and it's symmetric, is that A, for all scalars A and for all x and y in the algebra, A times B of x y is equal to B of ax y is equal to B of x ay, and then we have a linearity in each component, and the symmetry, so we can swap the entries. We call such an algebra an algebra over a field. However, in various subjects, it's sometimes necessary to consider algebras over objects more general than fields. And to that end, if R is a commutative ring, and A is an R module, and B is a symmetric R bilinear map, we call the triple RAB an R algebra, and refer to A as being an algebra over a ring. We say an algebra is unital if there exists a multiplicative identity element. And if it exists, it's necessarily unique, and I'll often write 1A to denote this. If K is a topological field, respectively a topological ring, then a topological K algebra or R algebra is when we have our algebra is a topological vector space, respectively topological module, and the multiplication operation B is continuous in some sense. Apparently, there isn't a single gold standard for what the notion of what the continuity of multiplication should be, but the most common requirement is that B is continuous in the standard sense, which is B as from map from A cross A to A is continuous as a map of topological spaces. In other words, for any open set U of A, B, the preimage of U under B is expressible as the union of products of open sets in A. This is also equivalent to requiring that every open neighborhood U of B's additive identity element, 0, satisfy this property when B of VW is the set of all x in A, such that x is equal to VW for some V in V and some W in W, where V and W are open neighborhoods of A's additive identity element. Regardless of whether our algebra is over a field or over a ring, since its multiplication operation is associative, it's a standard fact of abstract algebra that A will also be a ring. This is done by simply forgetting that A happens to come with a vector space structure. Instead, we then get A's ring addition operation from the vector space's addition operation, and get A's ring multiplication operation from the algebra's multiplication operation. If A is a topological algebra, we say A is locally convex if, as a ring, its topology is induced by a family of seminorms. Likewise, we say A is metrizable if, as a ring, its topology is induced by a ring norm. Note, every Banach algebra is a complete algebra over a field, but a complete algebra over a field need not be a Banach algebra. Banach algebra's norms are absolutely homogeneous with respect to a single absolute value on the underlying field. However, this is not necessarily true for a complete algebra. As an example, as we saw with C bounded of F, this has a ring norm which involves using lots of different absolute values, and so it wasn't going to be absolutely homogeneous. So this would be metrically complete, but it's not going to be a Banach algebra because its norm doesn't come from a single absolute value. So as an example, for a general global field K and a K-frame F on a set X, the spaces of compatible functions, bounded functions, and in the case that X is the periodic integers, the spaces of rising continuous and bounded rising continuous functions will all be topological K-algebras with respect to their ring-theoretic operations of pointwise addition and pointwise multiplication. This is done by equipping K with the discrete topology and by defining the product of a function with the scalar A as the product of the function F and the constant function from X to A. Since K has the discrete topology, every map out of K is necessarily continuous, which guarantees that whatever recipe we use to give our spaces a function of a topology, the topology of our ring operations will be compatible with the discrete topology on K. In the case of the simple p-q-adic frame, our rising continuous function space is then C rise of ZP QQ, the space of all functions from ZP to QQ, was satisfying our familiar limiting property. And of course, convergence is pointwise. As we saw in episode 7, this space is a Banach algebra over QQ under pointwise addition and pointwise multiplication, and its norm is the PQ-adic supremum norm. This is an example of a topological algebra over the field QQ, and the topology on QQ is not the discrete topology, but the Q-adic topology. This construction works verbatim if we replace every instance of QQ with any metrically complete extension of QQ. This is both for finite degree extensions as well as a CQ, the metric completion of the algebraic closure of QQ. It's also worth noting that if we equip K with a given absolute value to make K into a topological algebra over itself, there is no guarantee that this topological algebra will be a subalgebra of either the algebra of bounded functions or the algebra of bounded rising continuous functions. This is because, as we saw in episode 7, the F norm for a given K frame is not necessarily going to be multiplicative for scalars. That is, there can be, and in general will be, non-zero scalars A and B, such that the F norm of AB is strictly less than the product of the F norms of A and B. That is, even though K is going to be a non-topological subalgebra of C rising bounded of F and C rise of F, in the sense that we can consider its isomorphic copy in these algebras by taking the set of K-valued constant functions on ZP, the topology that this algebra inherits from these topological algebras via subspace will not be equivalent to the topology that K gets as a valued field. So that's a lot of technical jargon, and with that out of the way, because what matters here is because our spectral functions and our spaces of compatible functions and rising continuous functions are unital algebras over a field, we can do spectral theory with them. So let K be a field, and let A be a commutative unital K algebra. We say X is a unit of A if there is a Y in A, such that their X times Y is equal to the multiplicative identity element of A. It can be shown that Y is then unique, and so we'll denote it by X inverse. The set of units of A is denoted A cross, and this is going to be a group under multiplicative of multiplication, and we call the A cross the group of units of A. Given X in A, the spectrum of X is then defined as the set of all scalars such that X minus scalars lambda such that X minus lambda times the identity is not a unit. In other words, it's the lambda such that when we subtract off lambda identity, we lose invertibility. In functional analysis, the spectrum of X is traditionally denoted by sigma of X. However, since we will need a sigma to denote generic automorphisms of fields, I will write spec of X to denote the spectrum of X. So it's all lambda in K, such that X minus lambda times 1A is not a unit of A. The resolvent of X, denoted rho of X, and this is in keeping with orthodox functional analysis notation, is then defined as the complement of the spectrum of X in K. So, well, how does all of this jibber-jabber relate to chi-q? Well, as we saw, the rising continuous functions from the two adics to the q-adic complex numbers is a commutative Banach algebra over CQ with respect to the PQ-adic supremum norm and all our operations, and it is also, importantly, a unital algebra. The constant function 1 is its multiplicative identity element. Thus, the spectrum of chi-q is precisely the set of q-adic complex numbers lambda, such that 1 over chi-q of z minus lambda is not a rising continuous function. Of course, the spectrum of chi-q turns out to be precisely the image of chi-q over z2. More generally, we have that for any pq-adically rising continuous function f, the spectrum of f is simply equal to the f, if this image of f, what f does to the set of p-adic integers. And so for this, we just need to show that these two sets contain one another. So if lambda is in the image of f, then there's a z0 such that f of z0 minus lambda equals 0. So this function is then undefined at z0, and so as a result, it is not rising continuous because every rising continuous function is defined at every point of ZP. So that means if lambda is in the image, then the reciprocal of this is not rising continuous. Conversely, suppose that lambda is not in the image of f. Now for brevity, let's set g to be equal to 1 over f of z minus lambda. Since lambda is not in the image of f, this is going to be a well-defined function from zp to cq. As such, we can consider its nth truncation. By our truncation lemma, we have that this converges in q-adically to the Vanderput series for g, and the convergence is pointwise. In particular, this shows that this function here, the Vanderput series, is rising continuous. And so to conclude, what we're going to do is we're going to show that g is in fact equal to sp to its Vanderput series, which would then force g to be rising continuous, which then forces lambda to not be in the spectrum of f. So to see that g is in fact equal to its Vanderput series, let z0 be arbitrary. By the truncation lemma and the definition of gn, the Vanderput series of g evaluated at z0 is this limit, which is equal to this. And since f is rising continuous, this converges to that as q-adically. And in particular, since lambda is not in f of the image of f, then as n approaches infinity, the distance between f of z0 mod p to the n and lambda must be bounded from below. That is, there's some delta and an n delta such that this remains true. Actually, this shouldn't be for all n. This is just going to be for infinitely often, but whatever. So consequently, there's going to be n for which, and actually, no, it's not going to be no, actually, no, it is going to be for all n because this is going to converge to something else, which is not lambda. So this is bounded below by delta. And so if we pick n bigger than n delta, this difference, we then get this, and so this right here, this quantity is going to be independent of n, and here the implied, actually there's no constant, nothing implied, so since f is rising continuous, and since this is independent of n, the rising continuity means this quantity vanishes as n goes to infinity, and so if we pick n bigger than n epsilon, and the n needed for that, where n epsilon makes this thing small, we then get this, which is less than epsilon, since epsilon is arbitrary, blah, blah, blah. The limit converges, and so this sum is equal to that limit, which is equal to that limit, which is equal to this, which is by definition g of z0. And so therefore, g is equal to its Vanderput series, which means that g is rising continuous. Thus, the problem of studying the image of a rising continuous function is the same thing as studying the function spectrum in the algebra of rising continuous functions. Now we bring in the big result from episode 5. This was our PQ-adic Wiener-Tauberian theorem for measures. And so this was right here. Let F be an algebraically closed, metrically complete, non-Archimedean field of residue characteristic not equal to P, and let d mu be a measure, an F-valued measure on ZP. Then the following are equivalent. The span of with respect to f of the space set of translates of mu hat is dense in C0, and for any z in ZP such that this limit converges in f, the value of the limit is necessarily non-zero. Here I'm using this shorthand notation where mu n is the nth partial sum of the Fourier series generated by mu hat, and where we recall this is the linear combinations of functions of the form mu hat of t minus s, where s is a constant. So, as we saw, the summing of chi-q's Fourier series that we performed back in episode 1 told us that chi-q is quasi-integrable, and in particular, that chi-q can be identified with the 2q-adic measure chi-q of z dc, which we define by this formula, which we use our familiar Parseval-Plancherel formula. And here the sum is summed in CQ. So letting lambda be in CQ, we then have that chi-q minus lambda is quasi-integrable, and it's going to induce the following measure. And here we've just used the fact that the Fourier transform of a constant is constant times indicator function of 0. As such, our Wiener-Tauberian theorem yields the following. Let Q be an odd prime, and let lambda be a p-q-adic complex number, a q-adic complex number. Then the following are equivalent. The span of the set of translates of chi q hat minus lambda 1, 0 over the q-adic complex numbers is dense in the space of sequences from z2 hat to cq that decay q-adically to 0 at infinity. And moreover, for any z in z2 such that this limit converges, the limit is necessarily non-vanishing. So this is just a restatement of the p-q-adic Wiener-Tauberian theorem for measures in terms of concretely of this function. So now let z be in z2 prime, meaning that z has infinitely many 2-adic digits. Then we can, since the only term that this counts is when t equals 0, we can pull this out and we get as follows. And since this thing converges q-adically to chi q of z, we have that. And so, moreover, we saw that this thing failed to converge in CQ whenever z was in n0. Hence, 2 from this theorem implies that 1 is equivalent to the statement for all z in z2 prime, chi q of z minus lambda is not equal to 0. So we then have the following equivalences. The span of the translates is dense in C0 if and only if lambda is not in chi q of z2 prime. By applying the correspondence principle to this, we obtain what I like to call the Tauberian spectral theorem for the shortened qx plus 1 map, and that's as follows. Let q be an odd prime, and let x be a non-zero rational integer. Then, 1. If x is a periodic point of tq, the CQ span of the translates is not dense in C0. 2. If the CQ span of the translates is not dense in C0, then x is either a periodic point or a divergent point. And if x is a strictly pre-periodic point, then the span of the translates is dense. And the proof. So 1. If x is a periodic point, then the correspondence principle tells us that chi q of x, z is equal to x for some rational 2-adic integer z with infinitely many digits. Corollary 19 then tells us that this is the same thing as the translates having a span which is not dense. 2. If the span of the translates is not dense, then the corollary 19 tells us that x must be an element of this image, and so if x is equal to chi q of z for some rational element of this thing, the correspondence principle tells us that x has to be a periodic point. On the other hand, if x is equal to chi q of z for some irrational z in z2 prime, we then know that x has to be a divergent point. Thus, if the span that translates is not dense, x is either periodic or divergent. 3. Since 2 is true, its contrapositive is also true. The contrapositive of 2 is if x is neither a periodic point nor a divergent point of tq, then the span of the translates is dense. And since every integer is either a periodic point, a divergent point, or strictly pre-periodic, our contrapositive is the same as if x is a strictly pre-periodic point, then the span of the translates is dense, which is precisely 3. It's worth noting that the converse correspondence principle for divergent points, which I currently do not have a proof of, this is the statement that every divergent point of the shortened qx plus 1 map is the image of chi q. It's some irrational 2-adic integer. If we can prove this statement, if we can prove that statement, then the 3 conclusions of the Tauberian spectral theorem could be condensed into a nice single statement, namely, x is a strictly pre-periodic point if and only if the span of the translates is dense. In fact, we have the following. Let q be an odd prime. Then the following are equivalent. The converse CP-DP, in other words, every divergent point is the image of chi q at some irrational, and that is equivalent to the statement for any non-zero rational integer x, if the span of the translates is dense in C0, then x is a strictly pre-periodic point of tq. And so the proof is as follows. Suppose the converse for divergent points is true. So letting x be non-zero, we have that x is a periodic point if x equals chi q of z for some rational 2 adic z, and thus x is a divergent point if and only if x is equal to chi q of z for some irrational 2 adic z. Combining this, we have that chi q of z equals x for some z in z2 prime occurs if and only if x is either periodic or divergent, and then by the trichotomy of divergent points, periodic points, and strictly periodic, we then get that the converse CP-dP implies that x is the image of chi q at some element of z2 prime if and only if x is not strictly pre-periodic. Hence, if we negate both of these, we then get the equivalent that chi q of z is not equal to x for any z in z2 prime if and only if x is strictly pre-periodic. Since the Fourier series for this function converges in CQ if and only if z is in z2 prime, the Tauberian spectral theorem then tells us that this statement is equivalent to the density of the span of the translates. And hence, x is strictly periodic if and only if the span of the translates is dense, which in particular implies that if the span of the translates is dense, x is strictly pre-periodic, which is precisely the assertion of 2. Conversely, suppose the converse CP-dP is false. We need to show that 2, this guy, is false. And so to do that, since we have assumed that the converse CP-dP is false, there must exist a non-zero rational integer, which is a divergent point, but which is not a value that chi q attains at some irrational 2 adic integer. That is, x is not in the image of chi q of z2 prime, take away q. So if this happens, there are 2 ways it can happen. Either this is because x is equal to the image of chi q at some rational element of z2 prime, or that x is just simply not in the image of chi q over z2 prime at all. We can immediately discard 1 because of the correspondence principle for periodic points. If this happens, then x has to be a periodic point, but we assume that x was a divergent point. So the only way this can happen is if 2 happens. So for 2 happens, we know that if x is not in the image of chi q over z2 prime, then that means that the density of the span of the translates are dense, and so x is then a divergent point for which the span of the translates is dense. However, since 2 asserts that any divergent point for which this density occurs must be a strictly pre-periodic point, the fact that x is divergent rather than strictly pre-periodic is then a counterexample to 2. This proves that 2 is false when the converse CP-dP is false. Thus, the 2 statements are logically equivalent. So this is particularly interesting because this proposition then is the only non-trivial, non-tautological way to verify, potentially, that the converse correspondence principle for divergent points is true. In other words, if we instead attack this statement and show that it is true, we will then have proved a converse of the CP-dP, and then that would make everything nice, and we'd be able to simplify the Tauberian spectral theorem to this statement right here. So this is definitely something that, if could be shown, would be a wonderful boost for my theory. Yeah. With that done, now we're going to step into the real applications of this stuff, which is, I've named this near and far, and for the reasons you'll see in a moment. So, having now covered the Tauberian spectral theorem, we can actually start using it. So, to begin here, we're going to recall that this space of q-adically decaying sequences over Z2 hat can be given a Banach algebra structure in 2 different ways. The first is by defining multiplication to be pointwise. That is, f hat g hat times g hat is just their ordinary product. This is again going to be an element of C0, because if we apply the supremum norm, we get this, and since the supremum of a product is less than or equal to the product of the suprema, we get this thing. And so, since those are finite, this is finite, and this shows that multiplication is continuous. The other way of getting a Banach algebra out of this space is by using convolution, which recall the convolution of f hat and g hat is this sum of f hat of t minus s times g hat of s over all s. And just to be clear, we can actually prove this concretely. It involves doing a little playing around with estimates of tails of functions. For anyone who's interested, I'll just hold it here. So we start this, and then we go down here. Then I define this to be the tail and do some estimates. Then I use the ultrametric inequality. Then we let n get to infinity, and we get what we want. And the norm inequality follows from this, which is just a discrete ultrametric version of Young's convolution inequality. So as we saw in episode 5, the translates of f hat have dense span if and only if f hat is a unit of the convolution algebra. Indeed, this particular formula can be thought of as the limit of this finite sum, and here what we have here is quite simply a linear combination of translates of f hat. The coefficients then are just the values of g. So this density of the span here would mean that any h hat in C0 could then be written as this limit for some appropriately chosen sequence of family of constants Cs. In particular, since the 1, 0, the indicator function of 0, is the multiplicative identity element of our convolution algebra on C0, we see that the density of the span of the translates of f hat is equivalent to the existence of constants Cs, such that this limit converges q-adically to the indicator function of 0, and here it suffices for this to occur pointwise. So to analyze this situation in greater detail, I'm going to introduce the notion of what I call translation operators. So let P be a prime number, and let K be a metrically complete valued field with absolute value Q. I might also write this with a K, in which case replace every instance of Q below with K. Now, given S in ZP hat, I write tau S to denote the S translation operator on the space of bounded functions from ZP hat to K, and this is, as you would think, tau S of F hat of T is F hat of T plus S, and note that tau S is invertible, with tau S inverse is just tau negative S. A linear PQ-adic translation operator with coefficients in K is then a linear operator of the following shape. It's a linear combination of these elementary translation operators with coefficients in K. And here the TNs are constants in ZP hat, and I require them to be distinct. By the support of T, I mean these little TNs, and then I write trans P of K to denote the set of all PQ-adic translation operators with coefficients in K. If K is a global field, I might sometimes write the absolute value in there, where V is some valuation, in order to denote the specific absolute value that I've given to K. Note that if K is a number field and Q is a prime is a ordinary prime number, then this would mean that we equip K with the Q-adic absolute value subject to a given embedding of K in the algebraic closure of the Q-adic rationals. In this case, I will always state whatever embedding I'm using. So now two really important notations. Given a translation operator, I define the floor as the absolute value of the element of T's support with the smallest absolute value, whereas the ceiling of T is the element of T's support with the largest absolute value. So the next elementary proposition summarizes all of the important properties of translation operators. So first of all, the translation operator of 1, 0 is equal to Cn if T equals Tn, and is equal to 0 if T is not in the support of our operator. And so in particular, every translation operator can be written as T of 1, 0 of S times tau negative S summed over all S in the support of T. We could also make this sum over all S whose absolute values are less than or equal to the ceiling of T. So T is the 0 operator on the space of bounded functions if and only if T of 1, 0 is identically 0. Consequently, I'm going to say T is non-zero whenever its coefficients are all non-zero. Trans P of K is a vector space over K. Additionally, if we use k's absolute value, we then can get a norm on trans p of k, and this ends up being just the operator norm of t in the usual sense. And this is going to be an Archimedean or non-Archimedean normed vector space based on whether the absolute value on k is Archimedean or non-Archimedean. And in particular, if k is complete, then this is going to be a Banach space. Then this is just the standard estimate for continuous linear operators, and this is the other way of writing it. And also importantly, we note that composition of translation operators is commutative. And so where I adopt the convention of writing tau s, tau t to denote tau s of tau t. As such, we can make trans p of k into a commutative unital non-Archimedean Banach algebra over k by defining the multiplication of two translation operators as their composition as linear maps. The identity element is then the translation by zero, which doesn't change anything. And the proofs are all elementary. It's a fun exercise if you're not really comfortable with this stuff. Boop, boop, and boop. And then, of course, that's the career. Now, so with all these translation operators at our disposal, we can frame the density of spans of translates in terms of a much more tractable approximation problem. So let k be a complete valued field, and let f hat be a k-valued function on zp hat. Then, the spans of the translates of f hat are dense in C0, if and only if, for every epsilon greater than 0, there is some translation operator that such that t of f hat is within epsilon units of the multiplicative identity, or of the convolution identity in the PQ-adic norm. And so the proof is that for each translation operator t, this corresponds to a linear combination of translates of f hat. So this then leads to this useful terminology. Let k be a complete valued field, let f hat be the function, and let epsilon be greater than 0. Then I say a translation operator is an identity approximating translation, an IAT, of f hat of tolerance epsilon whenever t of f hat approximates the convolution identity to at most epsilon degree error in norm. In this language, we can restate our Tauberian spectral theorem in terms of IATs. Let q be an odd prime, and let x be a non-zero rational integer. Then, 1. The Tauberian spectral theorem was stated in 3 parts, so those are the same 3 parts. If x is a periodic point of the shortened qx plus 1 map, then for any sufficiently small epsilon greater than 0, this thing has no IAT of tolerance epsilon. If for any sufficiently small epsilon, this function has no IAT of tolerance epsilon, then x is either a periodic point or a divergent point. And if x is a strictly pre-periodic point, then for every epsilon, this function has an identity approximating translation. As with pretty much everything we've been doing so far, the reason for formulating our Tauberian spectral theorem in terms of IATs is due to the leverage we get from chi-q's functional equations. To begin, we note that, as one would expect, chi-q's functional equations translate, pun intended, to functional equations for chi-q hat. Notably, these equations are independent of the choice of the representative of the equivalence class of functions that are Fourier-Stieltjes transforms of chi-q. Just as a reminder, when we have a quasi-integrable function like chi-q, its Fourier transform is not uniquely defined. Rather, it is only unique modulo a degenerate measure, which is one whose Fourier series converges to 0 pointwise everywhere with respect to the frame with respect to which our function is quasi-integrable. So our next step comes from making a key observation about chi-q hat's translates. As a test case, let's consider chi3 hat of t plus 1/2. Using our formula for chi3 hat for non-zero t, we get this. Here's where the ultrametric structure of z2 hat comes into play. Note that when t has a 2-adic absolute value, so this should be a 2, not a 1/2. When t has a 2-adic absolute value strictly greater than 2, The ultrametric inequality tells us that v2 of t plus 1/2 will just be the same thing as v2 of t, because v2 whatever one of these has the larger absolute value will be the one that dominates. This also affects a3 hat as well. If we add a 1/2, the upper limit of multiplication reduces to negative v2 of t if t2 has a 2-adic absolute value greater than 2. And so that is, we get, this formula becomes this thing. Now the trick. We're going to multiply and divide the right-hand side here by a3 hat. And when we do that, we get this thing. And this is true whenever, this should be at 2, and this should be at 2. For all t with denominator bigger than 2. Here, when t has denominator bigger than 2, this is going to be, actually this is strictly greater. And so this product is going to range over n from n up to at least 1. And so we have this thing. And here we note that when t has a denominator bigger than 2 and m is greater than or equal to 1, the 2 to the m will simply kill the 1/2. And so we end up with, just to watch where things go, here we pull out the first term and then the next terms, and then this thing, because for m large, this is just going to be 1. And so we end up with this. I'll leave that here for a bit. And so, in summary, when we multiply things out and simplify this, we end up with the following relation. Chi3 hat of t plus 1/2 is equal to this times that, which simplifies, and we end, and noting that this is, of course, just chi3 hat of t, we get that chi3 hat of t plus 1/2 is equal to some rational function of e to the 2 pi I t times chi3 hat of t, provided that t has again, this should be 2. In other words, we have this rational function such that we have an identity of this form. What's crucial here is that this property holds in much greater generality, and this motivates the following definition. Let P be a prime, let K be a field, and let K be a chi hat be a k-valued function on ZP hat. I say chi hat is shift multiplicative if for every non-zero s in ZP hat, there is a rational function rs of x with coefficients in k, such that chi hat of t plus s is equal to rs of e to the 2 pi I t times chi hat of t for all t bigger than s. And I call this the shift factor of chi hat at s. So a shift, ignore this. This is my computational detritus. These functions have some important properties. The pointwise product of two shift multiplicative functions is shift multiplicative. If chi hat is shift multiplicative and its support is infinite, then the shift factor the shift factors are unique. And if chi hat is shift multiplicative, then chi hat of t plus c times the integrator function of 0 is shift multiplicative for all scalars c, and its shift factors are chi hat shift factors. The proofs: 1, if chi hat and delta hat are shift multiplicative with shift factors rs, big Rs and little rs, we get this, and so therefore the shift factor of the product is the product of the shift factors. 2, let chi hat be as given, and suppose that there are two rational functions, big Rs and little rs, such that this holds when t is bigger than s. Then, of course, we set these two equal to one another, and we get the following for all t bigger than s. And so, since we assume that chi hat has an infinite support, there's infinitely many t, in particular infinitely many t bigger than s, for which chi hat of t is non-zero. So for all of those t, we divide by chi hat of t on both sides to get this. So what this means is that if we have writing rs and big Rs and little rs as rational functions like so, this equation, the equation rs equals little rs, can be written as ps equals 0, where ps is this polynomial. So this thing, for all t greater than s, for which chi hat of t is non-zero, implies that ps is 0 for at e to the 2 pi I t for all t bigger than s. But then that means that if we consider the algebraic closure of k, this means that ps is a polynomial whose coefficients are in k, which has infinitely many roots in the algebraic closure of k. But that's impossible because the only it's impossible unless p is the zero polynomial, because any non-zero polynomial over a field necessarily has finitely many roots over the field's algebraic closure. So since p is identically zero, big R and s and little rs are identically zero as polynomials, which then proves the uniqueness of chi-hat shift factors. Finally, for the shifting by a multiple of the convolution identity, if rs is the s shift factor of chi-hat, note that when t is bigger than s, 1/0 of t plus s is always going to be 0, because the only case where this can be equal to 1 is if t is equal to negative s, and in particular, if t has the same size as s. So chi-hat of t plus s plus c times convolution identity of t plus s is equal, this thing vanishes, and we get this, which is just that, and then just as it vanished, we can make it appear all over again, and we're done. So now we're going to show that chi-q hat is shift multiplicative. I'm going to do this in 2 steps. So first, let chi-q hat be any Fourier transform of chi-q. Then for any any positive integer n, we have that chi-q hat of t plus 1/2 to the n is equal to chi-q hat of t times this rational function, provided t's denominator is strictly bigger than 2 to the n. The proof is we just first use our formulas for chi-q hat and look at this quotient, which we get these two things. Here, by the 2 Adic ultrametric inequality, since t's absolute value is bigger than 2 to the n, this equality occurs. And so here, when q is greater than or equal to 3, this becomes this, and here I'm just writing a c2 to the c subscript something is my shorthand notation for e to the 2 pi I over something. So here, note that when k is bigger than n, this root of unity is going to be 1. And so the kth term of the product here on the right is 1 whenever k is greater than or equal to n and less than or equal to this. So we then are left with the following. And you have to also note that here, because of this fact, these two quantities cancel to become 1. So that's just the proof that I was doing before, said much more cleanly and distinctly. And so now we have the shift multiplicativity. In particular, the s shift factor of chi-q hat is rs equals this product here. And so what we're going to do is, for every given s, let al of s be the coefficient of 1/2 to the l in the binary expansion of s. Here, s, remember, is a rational number in the unit interval, which is a dyadic rational. And here, so what I'm saying is we take s, we write it in binary, and then we multiply by the r subscript, where this is going to be r0 if ak of s is 0, and is going to be r 1/2 to the k if ak of s is equal to 1. And then we evaluate this at e to the 2 pi I times 2 to the k s's 2-adic fractional part, and then we divide by 2 to the k. And the proof, and here we use, of course, that r0 of x is equal to 1. And the proposition is just, we go by induction. So from the previous proposition, this is what we had for r2 to the negative n. So now let's consider a strictly decreasing sequence. A strictly decreasing sequence of integers. And then so by induction, since n1 is bigger than n2, and we proceed by induction using this thing, etc. And so the whole point is that any s can be written as a sum of this shape, where we have strictly increasing or decreasing. We get this, and then we just do some manipulations, which I'll just stick, and we're done. To make this particularly nice, we can observe the following. here we'll let little p0 of x be the constant polynomial 1, and for every n bigger than or equal to 1, we'll let little pn of x be the product of x 2 to the k plus q from k equals 0 to n minus 1. And now we have the following lemma. Rs of x is equal to e to the 2 pi is times p times negative v2 of s, e to the 2 pi is x over p negative v2 of s x. In other words, the p here, the exponent here is just going to be the exponent of 2 in the denominator of s. And the proof, we start with r of 1 over 2 to the n. And you just go through it. We factor out the root of unity here. We do the sum. We pull out the 2 to the k, and we get what we wanted. For the rest, for the next part, this is messy. In general, ak of s over 2 to the k is equal to this. And note the reason why this all works is that if a of s is equal to 1, this is going to reduce to the identity that we just proved right here for k. And if a of k of s is equal to 0, then this becomes 1, and the whole thing reduces to 1, which is exactly what we defined R0 to be. So letting ck be this particular sum, with ck being 1 whenever k is greater than negative v2 of s, we just manipulate our product, we carefully re-index, blah, 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 and then note that ck multiplied by 2 to the k ak of s plus 1 is equal to ck. And finally, the key thing to note is that we have this recursive relation between the pk's, which when we plug it into this by a miraculous re-indexing, here we rewrite this in terms of pk minus 1. Then we shift here the re-index at this step to make k decrease by 0 and decrease by 1 and decrease by 1 there. And then it's the multiplicative version of the Ramanujan sum trick that we use when summing our Fourier series to exploit cancellations. So when we pull out the boundary terms to make everything line up, blah, 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 re-indexing, and we get what we want. So here now we're going to start. Let's consider a translation operator T of this shape, and then using the shift multiplicativity of chi q hat, and therefore of this function, observe that when t is bigger than 2 to the n, in other words, when t is bigger than the ceiling of t, of our operator, we can do as follows. We apply t to this function that looks like this. Here, since t is bigger than 2 to the n, and since s is less than or equal to 2 to the n, this quantity right here is always going to be equal to 1, 0 of t, because t is bigger, so whether or not this is 0 depends only on what t is. So and in particular, in fact, this is never going to be 0, so this whole thing just disappears. And then we have that t of chi q hat of t. This thing, we use our shift multiplicativity, and we get this. So, in other words, when t is larger than the ceiling of our translation operator, the translation operator applied to this function ends up acting like a multiplication operator, like a Fourier multiplier. So if in an abusive notation I write tr of x to denote this particular rational function, we then get the following. Let t be a translation operator and let x be an integer. Then t of chi q hat minus x bold 1 of t is equal to the rational function of e to the 2 pi I t times chi q hat of t for all t whose denominator is bigger than the height than the ceiling of t. Because of this, observe that when t's denominator is bigger than the ceiling of t, the extent to which this function approximates the convolution identity is independent of x. And so recall what we wanted to do was to examine whether or not, given an x, we could find t which was an identity approximating translation for this function of tolerance epsilon. That is, we need this inequality, q-adic absolute value, to occur for all t. When t is bigger than the ceiling of t, this thing reduces to just that, and so we then end up the following. We have that chi q hat minus x 1, 0 has an identity approximating translation if and only if of tolerance epsilon, if and only if the following happen. First, for all t bigger than the ceiling of our translation operator, the rational function of e to the 2 pi I t times chi q hat has a q-adic absolute value less than epsilon. And if, in addition, for all t less than or equal to the ceiling of our operator, this approximation occurs. In other words, solving the identity approximating translation problem for a given x is actually two problems in one. One problem which is dependent on x, and one problem which is completely independent of x. I call these the near equations, this is the near equation, and the far equation, respectively. And so let's see here. So I think I'll just introduce the terminology now. So let epsilon be greater than 0, and let chi hat be a bounded k-valued function on Z2. This should be Z2 hat, where k is a non-Archimedean valued field. Then I say that a translation operator t is a near identity approximating translation, NIAT, of tolerance epsilon, whenever this approximation holds for such t. I call these t, I say that they are near values of t, or the near regime. So given a translation operator, the near regime of our t's are those t's whose 2-adic absolute values are at most the ceiling of the operator. And then so I call I say that solving the near identity approximation problem means finding a translation operator which satisfies this inequality for all near values of t. On the other hand, a far identity approximating translation, an FIAT, is one which solves the identity approximation problem whenever t has an 2-adic absolute value which is strictly greater than the ceiling of our operator. I call such t, this is the far regime of t. So given our translation operator, t is our lowercase t is near if its 2-adic absolute value is less than or equal to the ceiling of the translation operator, and little t is far if its 2-adic absolute value is strictly greater than the ceiling of the translation operator. And then, of course, so we then have the far identity approximation problem. And again, I call this the far equation, and then this is the near equation. Yeah. So if there is a t which solves both the far identity approximation problem and the near identity approximation problem, I then say that t solves the identity approximation problem for chi hat, and obviously any identity approximating translation of chi hat is necessarily going to be both a far and near identity approximation translation. Also, technically, if I say valuation tolerance, it means of tolerance. Valuation tolerance n, it means of tolerance epsilon, where epsilon is equal to q to negative n. So, additionally, given t, I speak of this. As I say, I speak of the near regime, far regime. And so then we have the following: that let chi hat be shift multiplicative with this shift factor. Then we have a far identity approximating translation if and only if our rational function is less than or equal to epsilon over the q-adic absolute value of a chi q hat for all far t. And this, of course, is immediate for the definitions. I will get to this later, but this particular inequality is rather interesting because it shows a connection to our observation earlier that if we consider chi q hat here, as we saw, chi3 hat was unique in that its 3-adic absolute value would get arbitrarily close to 0 infinitely often. However, for chi-q hat, for q greater than or equal to 5, that function always had a q-adic absolute value of 1. So what happens here is when we are considering chi3, the bottom term here will get arbitrarily small infinitely often, which means that there's going to be values of t for which this upper bound is quite large. Where, on the other hand, if q is greater than or equal to 5, chi q hat, this will always be equal to 1 in q-adic absolute value. So I think that this is one of the reasons why I think that the boundedness away from 0 is super important, because we see that when we have boundedness away from 0, the only way to get a nice solution to this problem is to have a t which makes everything small. However, if our chi hat is not bounded away from 0 q-adically, then there are going to be t for which this quantity could be extremely large, and yet we still have a solution to the Farr equation. So if we were going to prove that there is indeed a connection between the boundedness away from 0 of the Fourier transform of the Newman and the existence of divergent points or whatever, you would then need to show that the ability to solve the identity approximation problem in order for there to be many solutions to that, which means few points which are not strictly pre-periodic, you would need to have a lot of wiggle room, and that if you don't have enough wiggle room, then there's going to be lots of values for which the density, for which the identity approximating translation problem doesn't have a solution, and thus you're going to expect that there are going to be lots of periodic and or pre-periodic points. So in this mindset, I like to think of this setup as being kind of a constrained optimization problem. The Farr equation is its solution or lack thereof depends only on chi q hat. It has nothing to do with the values of x with the spectrum. However, it's the near equation where x comes into play. So in other words, our constraint here is the Farr equation, and then the thing we need to solve or optimize is the near equation. Yeah. So note that when we write out the left-hand sides of the near equation and Farr equation, we end up getting a system of linear congruences. Writing epsilon equals q to the negative n, this inequality, which again this needs to hold for all t, if and only if we solve the identity approximation problem. This is the same thing as the following system. At 0, we get that it's congruent to 1 mod q to the n, and away from 0, we get that it's congruent to 0 mod q to the n. So if we let f hat denote this guy, we can write these equations as so. And here the CS's, which are the coefficients of t, are our unknowns, while the values of f hat are the coefficients. Thus, so what we're ending up dealing with is we're trying to solve a system of congruences, which is, and really this is quite affirming that we're on the right track, because it gives us an immediate parallel to transcendental number theory. In that subject, one of the key methods is based on the famous Siegel's lemma, the other much more famous and talented Siegel, C.L. Siegel, as opposed to yours truly. And Siegel's lemma is an existence lemma, which gives conditions on rational solutions to a system of m linear equations with rational coefficients in n unknowns, where n is strictly bigger than m. This is intimately related to the ancient topic of Diophantine approximation, the approximation of irrationals by rationals, the Siegel-Thu-Roth theorem, and Schmidt's storied subspace theorem and its many generalizations. So this is where we're starting to actually get into something that looks like transcendental number theory, which is that in order to deal with these near and far equations, we are considering systems of congruences. The difference then is that and this is important, classically when you're using Siegel's lemma, such as when you're using a Baker's theorem and other methods like that, what you do is you are approximating things in the Archimedean absolute value. However, for us, we're going to be using the Q-adic absolute values. So next we'll make some basic observations about our equations. So for brevity, again, I'm going to write fqx hat to denote our eigenvalue function. So as we've seen, our goal is to understand which, if any, t's result in t of f hat of qx being a q-adically good approximation of the convolution identity. That is, we wish to understand the infimum of t over all translation operators, over from two q-adic translation operators, the infimum of t of f hat qx minus convolution identity. For the sake of discussion, let's assume that the full correspondence principle, periodic and divergent points alike, is true. Then we'd have that this infimum will be 0 if and only if x is a strictly pre-periodic point. However, since the convolution identity vanishes when its input is non-zero, note that we can do the following. So here's the definition of what our supremum norm is. And then we use the fact that when you make a set smaller, the supremum over the set gets smaller. We're going to remove 0. Now that we've removed 0, this dies, and so we're left with this. So if this norm can be made arbitrarily small by choosing an appropriate translation operator, such a choice is necessarily going to make this value arbitrarily small too. Moreover, this argument here, this is true for any function, not just qx hat. On the other hand, the converse of this is not at all true. If we take t to be the 0 operator, then this supremum is clearly 0, while, on the other hand, this is equal to 1, which is about as far away from a small epsilon as you can get. So, while this choice of t is obviously degenerate in a trivial way, it is vital to note that we do not need to make t the 0 operator in order to get degenerate behavior. In particular, let's fix some bounded 2q-adic function over z2 hat whose norm is non-zero, so this function is not identically 0. Now let's suppose that we pick a translation operator whose coefficients are all q-adically small. Say that the norm of t, this is also its norm in the space of translation operators. Suppose this norm is less than or equal to epsilon over whatever chi hat's norm is. Then, by the fact that this is a continuous linear operator, we get that t of chi hat has a norm which is less than or equal to epsilon. So, such a t will then necessarily satisfy this equation, this inequality, for all non-zero t. Moreover, since t of chi hat is the supremum of t of chi hat of little t over all little t, we then have that the t of chi hat of 0 will be less than or equal to epsilon. Why is this significant? Well, if epsilon is strictly between 0 and 1, then the ultrametric inequality tells us that this has to be equal to 1, seeing as this function right here equals 1 at 0. So, in other words, because the indicator, the convolution identity, takes a value on the q-adic unit circle when t is 0, the only way for this equality to occur is if t chi hat of 0 also lies in the q-adic unit circle. If, say, chi hat's q-adic absolute value is equal to 1 for all t, the only way for t of chi hat of 0 to lie in the unit circle is if at least one of t's coefficients lies in the q-adic unit circle. If all of the t's coefficients have q-adic absolute value strictly less than 1, t of chi hat will never be able to nicely approximate 1, 0 in 2 q-adic norm. So you can think of this is that what we're really saying here is that we cannot have t's coefficients all be q-adically small. Or if we think about this, there cannot be a value of n such that t is equal to the 0 operator modulo q to the n. because if that occurs, then although t will solve the far equation, it will never solve the near equation because t will be very small at 0, but 1, 0 will be large at 0. So because of this, we have the following definition. Given a bounded chi-hat and an epsilon strictly between 0 and 1, suppose that t is a far identity approximating translation for chi-hat of tolerance epsilon. Then I say t is non-trivial whenever t's norm is strictly greater than epsilon over the norm of chi-hat. So the idea here is that a trivial FIAT solves the far equation simply by making everything small. A non-trivial solution, meanwhile, is one that makes things small by exploiting cancellations among the translates of chi-hat. So the proposition, given chi-hat and epsilon between 0 and 1, let t be an identity approximating translation of chi-hat of tolerance epsilon. Then t is a non-trivial FIAT of tolerance epsilon. So the proof, let everything be as given. Since t is a IAT of chi-hat of tolerance epsilon, it is an FIAT of tolerance epsilon as well. To see that t is non-trivial, suppose by way of contradiction that this is trivial. This should be less than or equals. Then we have that t's norm is less than or equal to epsilon over the norm of chi-hat. Hence, every coefficient of t has q-adic absolute value less than or equal to this quantity. And so we get t of chi-hat of 0. Its q-adic absolute value is the q-adic absolute value of this. We apply the ultrametric inequality to get this. We then, the q-adic absolute, the norm of t is the supremum of all of the CS's. And then here, this is, of course, just the norm of chi-hat of s. And then, since we assumed that t was trivial, this is less than or equal to epsilon over the norm of chi-hat, and so blah. But then we get that this is less than 1, but then the ultrametric inequality tells us that this is equal to 1, which contradicts the fact that that as an IAT, this quantity should be less than epsilon for all t, including t equals 0. So every identity approximating translation has to be non-trivial. So returning to the far equation for chi-q-hat, our requirement is that our rational function is less than or equal to epsilon over the absolute value of chi-q-hat for all far t. Unlike the example we considered above, the upper bound here varies with t rather than being uniformly bounded. And so this gets back to that issue I was talking about, where the boundedness away from 0 of this, or lack thereof of this, is important. So in line with the idea that the IAP is a constrained optimization problem, we can use the fact that the far equation's solutions, or lack thereof, is independent of x to obtain a space of admissible translations from which any identity approximating translation must be drawn. And so just as terminology, when I'm considering neighborhoods of 0 in Z2 hat, I have two different enumerations, actually 3 different enumerations. The denominator enumeration is where I list things in an order of increasing denominators and then increasing numerators with respect to a given denominator. The numerator enumeration, on the other hand, is where everything has denominator 2 to the n, and I just list the numerators in strictly increasing order. The reverse denominator enumeration, meanwhile, is where we enumerate them by increasing denominators, but then for any given denominator, we enumerate the elements of that with decreasing numerators. And so here now is our big proposition, and I think I will end this episode with it. So this part of this episode with it. So let x be a rational integer, let n be in a rational integer positive, and let kn denote the cyclotomic field obtained by adjoining a primitive 2 to the nth root of unity to the rationals. And then we're going to equip this with the q-adic absolute value, and we're going to embed it in the q-adic complex numbers in the manner that we discussed in episode 6, I think it was, where we define the e to the 2 pi I over 2n. Its value, mod q, is going to be the smallest positive integer, which is a primitive 2 to the nth root of unity modulo q. So assuming that such a thing exists. Then there is going to be a translation operator, T in n in Kn, satisfying the following properties. The ceiling of over 2 times the base 2 logarithm of the ceiling of T is greater than or equal to n. T will be a non-trivial far identity approximating translation of fqx hat of valuation tolerance n. And specifically, there is an S in the support of T, this shouldn't be scripty, so that CS, the S coefficient of T, has a q-adic absolute value strictly greater than q to the negative n. And then the rational function that we got, T of R, is less than or equal to q to the negative n for all q-adic complex numbers which are not on the poles. So the most important part is probably this one right here, which is, because think about it like this. If for this to be a identity approximating translation for the far equation of tolerance n, of valuation tolerance n, it means everything is going to be at least q to the n, q to the negative n small. So in order for T to not be trivial in this context, what we need is for there to be at least one coefficient of T which is larger than the value of T of fqx hat over the far regime. And so this ends up boiling down to examining the determinant of a certain matrix. So let everything be as given. Let T be an arbitrary translation operator. And again, the Q shouldn't be here. For brevity, let M be the integer such that the ceiling of T is equal to 2 to the M. What we want is that T of fqx hat is going to be small in the far regime. Since fqx hat is shift multiplicative, if we want T to be a far identity approximating translation of valuation tolerance n, what we're going to need, of course, is this equation for all T in the far regime. Since fqx hat has a norm of 1 for all x in Z, note that the smallest value the upper bound can attain here, as T varies, is q to the negative n. As such, a T satisfying this thing here, it will automatically satisfy 8.18 and therefore be a far identity approximating translation of valuation tolerance n. The non-triviality condition, on the other hand, is that the norm of T is greater than q to the negative n over the norm of fqx hat, but this norm is just 1, so this what we then require is that the norm is strictly greater than q to the negative n, and since T is the maximum of the q-adic absolute values of the coefficients, the CS's, the requirement that T's norm is strictly bigger than q to the negative n is the same thing as saying that there exists an S less than or equal to the ceiling of T, such that CS is not a multiple of q to the n. Thus, to complete the proof, we need to show that there is a T satisfying this condition, for which CS is not a multiple of q to the n for some S less than or equal to 2 to the m in absolute value. And here we'll also need, there needs to be a certain relationship between n and m, as we will see. So to do this, we're going to write out 8.19 here as a system of congruences. This, of course, is just this thing, and here the CS are our coefficients of T are the unknowns. Thus, we have a system of infinitely many linear congruences, modulo q to the n, but with only 2 to the m unknowns. Obviously, we could solve this by making all of the C's 0 mod q to the n, but then T would be trivial, so we can't do that. So because this system is overdetermined, the only way we'll have a non-trivial solution is if little t actually has no bearing in this. And that is to say, we have that the rational function tr of x itself is a multiple of q to the n as a rational function independent of what value we happen to evaluate it at. That is, what we're examining is this congruent to 0 mod q to the n. Now, first step is after clearing the denominators, this congruence is going to become a congruence of the following form, where the PSMs are the following polynomials. These are the modified versions of the little p's from before. So to see that the proof of the claim, to see that these polynomials actually have this shape, we're using our lemma here, which gave us a rational expression for the shift factors. Here we sum over all the s's, and we'll pull out the s equals 0 term, and we then are going to sum over s's with constant, with over the level sets of s's with a fixed 2 Adic absolute value. Here, we note that Pm will divide Pn whenever n is bigger than or equal to m. So we can then clear both sides of this by multiplying them by P big M. This gives us the following. Here, we note that P big M over P little m is that guy. So we have this. And now something fun. Here, e to the 2 pi is x to the 2 to the k is going to be equal to just x to the 2 to the k whenever k is bigger than the exponent in the denominator of s. So when s has a 2 Adic absolute value of 2 to the m, we have this thing here is equal to this thing, and I'm inserting the e to the 2 pi is. This, meanwhile, is just the definition of this guy. Here, we go from k equals m to big M minus 1, and here we go from k equals 0 to m minus 1, so these two stitch together, and we get one function. So we get this, and here, since we no longer have dependence on little m or s on the subscript of the polynomial, we have the following. And finally here, we just write out the formula for P big M. That's this thing. I'm then going to pull out e to the 2 pi I 2 to the ks, sum the series right there, then those two cancel. This cancels with the negative 1, leaves us with e to the 2 pi I s 2 to the m, but since s is 2 radically less than or equal to 2 to the big M, that e to the 2 pi I s 2 to the big M vanishes to 1 as well. Excuse me. And so that goes away, and we're left with this, which is precisely PSM. So that gives us the desired form, and that proves our claim. So now note that PSM of x contains our favorite generating function, which is 1 plus the product from k equals 0 to number of 1 plus something to the 2 to the k. When we multiply this all out, we get this right here. So, as we've seen, after clearing denominators, this congruence will occur whenever this congruence occurs, and if we just reorder the sums and rearrange things, we get this. So this again is a congruence of polynomials. So the x's are just formal indeterminates here. So the only way that this occurs, of course, is if the coefficient of x, of every power of x, is 0, modulo q to the n. So that means this is going to happen if and only if this sum is congruent to 0 mod q to the n for all k from 0 to 2 to the m minus 1. This is a system of 2 to the m linear congruences indexed by k in 2 to the m unknowns. So it's a square, and it might have a solution. We're going to write C to denote, bold C to denote this 2 to the m by 1 column vector. Here we're using the denominator enumeration. The matrix version of this system is then AMC, where 0 is the 2 to the m by 1 column vector of zeros, and AM is the matrix whose terms are indexed by S and K, where K indexes the rows of AM, and S indexes the columns of AM, and the individual columns are listed according to the denominator enumeration of S. As an example, A2, 1, 1, 1, 1, Q, negative IQ, IQ, QQ, negative Q, Q squared, negative Q squared, IQ squared, negative IQ squared. So we can, by inspection, we can then write AM as the product. AM equals DM UM, where DM is the diagonal matrix whose diagonal entries are Q to the negative 1, Q to the number of 1s in K, and where is a matrix of roots of unity indexed by S and K in the same way that AM is indexed. As an example, when M equals 2, we have this. Here, we note that U2 is a Vandermonde matrix generated by the fourth roots of unity. More generally, we have that UM is the Vandermonde matrix whose nth column, starting with n equals 0, is the nth. So we have that UM is equal to Vandermonde of 1 second root of unity, 3/4, 1/4, 7/8, 5/8, blah, 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 1/8, blah, 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 2 to the m minus 1, 2 to the m, blah, 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 2 to the m. Note that it takes 2 to the m minus 1 swaps to rewrite this reverse enumeration for a fixed denominator as the straightforward enumeration. We have that for m greater than or equal to 2, it takes this many swaps to rewrite this as in the strictly increasing order. Thus, the determinant of is equal to -1 to the 2 to the m times m minus 1 over 2 times the determinant of the Vandermonde matrix generated by the roots of unity listed using the denominator enumeration. Using the well-known formula for the determinant of a Vandermonde matrix, we get this, and a long and arduous computation of that reveals that up to a factor of a root of unity, the determinant of is 2 to the m times 2 to the m minus 1. Since dm is diagonal, its determinant is just the product of its diagonal entries, which is this sum, where we use this identity, which is easily verified by the recursive method. We then have that for any prime number L, the L-adic absolute value of the determinant of AM is the product of the L-adic absolute values of DM's determinant and UM's determinant, which is then, of course, this is Q to the m 2 to the m minus 1. This is 2 to the m to the 2 to the m minus 1. And so then this tells us that the determinant of AM has a Q-adic absolute value of Q to the negative m to the 2 to the m minus 1. So, in other words, in order to make the determinant of AM 0 modulo Q to the n, it suffices that we choose m and n so that n is less than or equal to m times 2 to the m minus 1. This is where the that logarithm condition on the ceiling of t comes from. To use this now, we note that since AM will have entries in Q adjoin 2 to the mth root of unity, we can embed this in QQ of adjoin 2 to the mth root of unity, and then project down to the ring RMN is ZQ adjoin 2 to the nth root of unity modulo Q to the n ZQ adjoin 2 to the nth root of unity. As an RMN linear map, AM will be invertible on RMN, that is, AM will be invertible mod Q to the n, if and only if the determinant of AM is a unit of RMN. Since the determinant of AM vanishes mod Q, provided that n and m satisfy that relation, we then see that this condition is sufficient to guarantee that the kernel of AM over RMN is non-trivial. So this condition is then equivalent to the existence of a C with entries in QQ adjoin 2 to the nth root of unity, so that AMC is congruent mod Q to the n to 0, but that not all of C's entries are congruent to 0 mod Q to the n. So that means this C then has to have at least one entry which has a Q-adic absolute value which is strictly greater than Q to the negative n. So this C then corresponds to a non-trivial choice of T. That proves 2, and then the condition 1 comes from using the ceiling is just 2 to the m. And finally, for this particular T, we saw that this holds true in the field of rational functions with coefficients in QQ of adjoin 2 to the mth root of unity, and so this will hold true as well when we evaluate it at any Q-adic complex number Z, provided that it is not a pole of any of the rational functions, and so we then get that this is going to have a Q-adic absolute value less than or equal to Q to the negative n, and that takes care of all of that. Let's see, how much more do I have to go with this? Actually, no, it's not that much more, so we can finish quickly. So yeah, let's just finish up. So now going with all of this, blah, blah. So we had that, and we finished that. So now fix a t. We then write bold CT to denote the column vector whose entries are the coefficients of t, where we're writing them where s goes using the ordinary denominator enumeration. I then write AT to denote the matrix so that this system is then represented by ATCT. We then write that AT is written as DT-UT, just like the proof of the above. And as such, we will write AM and DM and UM to denote all these matrices when they occur, in the case when T's ceiling is 2 to the m. All these matrices are going to be 2 to the m by 2 to the m. So, lemma now. Let x be an integer, let n be a positive integer, let t be a translation operator. Then t is a far identity approximating translation of tolerance q to the n, if and only if this is true, which we just saw in our proof of our big proposition. And then so now we have the following. Let x be and n be as before, and then t will be a solution. And suppose t is an identity approximating translation for fqx hat, letting of its evaluation tolerance n, and let m denote the log of the ceiling of t. Then m2 to the m minus 1 is greater than or equal to n. The norm of t is strictly greater than q to the negative n, and the vector ct is a non-trivial element of the kernel of am mod q to the n. This is just a restatement of everything we've had before. Now the fun part. So UM is a normal matrix. That is, it commutes with its conjugate transpose. So now I'm just going to stop myself for a moment. A second ago, we were working in Q-adic world, but now I'm talking about conjugate transposes, which is something very much belonging to Archimedean complex analysis world. What the hell just happened? Why are we doing this strange jump? And the answer is, this is because chi-q hat takes values in algebraic numbers, namely it outputs values that are in the maximal 2-power cyclotomic extension of the rationals. As a result, even though we're analyzing our matrices in Q-adically, the reason why we're doing that is because we've embedded these algebraic numbers into the Q-adics. And so we can stop and look at these things from the Archimedean perspective. And actually, just as an addendum, one really interesting question that I haven't really explored that much is, how can we potentially approach this problem rather than just by looking at the Q-adic absolute values and Q-adic norms, but do it rather adelically? That is, we use the product formula, which then tells us that that all of these congruences, etc., are going to be related to the congruences modulo powers of all the other primes of whatever cyclotomic field we're working in. So that is to say, rather than to study the problem of identity approximating translations Q-adically, we could try to approach it by studying them L-adically for all the primes L of the field that T has its coefficients in, and then try and show that maybe that we can get control over them for enough of the primes L that we can then get our estimate that we want. Again, this is just all speculation on my part, but it's an interesting thing because, again, we're not just confined to working in the Q-adics. We have access to all of the other completions of the cyclotomic field because the measures we're working with, their Fourier transforms, take algebraic values. So UM, we're going to show it's a normal matrix. And so in particular, since UM is a normal matrix, it now follows by linear algebra that UM will be unitarily diagonalizable. That is, it is matrix conjugate to a diagonal matrix, and the conjugation matrix is unitary. Its inverse is its conjugate transpose. In particular, UM times UM UM dagger, where dagger is conjugate transpose, is then equal to 2 to the m times a 2m by 2m identity matrix. And so in particular, we have that um's inverse is um dagger over 2 to the m. And the proof, we just use the discrete Fourier transform. The nth discrete Fourier transform matrix, the DFT matrix, is defined by bold Fn is 1 over the square root of n times the Vandermonde matrix generated by the nth roots of unity, and the nth roots of unity enumerated according to the numerator enumeration. It is common knowledge that Fn is a unitary matrix, meaning that it is invertible, and that its inverse is Fm dagger. A quick computation shows that there is a permutation matrix e to the m, so that em, em inverse is equal to the Vandermonde generated by the 2 to the mth roots of unity, which is then equal to the square, using this formula, it's the square root of 2 to the m times f2m, which is 2 to the m over 2 fm. So what this then tells us is that um over 2m over 2 is similar to, i.e. conjugate to, a unitary matrix, which then makes it a unitary matrix on its own. So that means that um over 2 to the m over 2, its inverse is equal to its conjugate transpose. And working through the math, we see that um inverse is um dagger over 2 to the m. So then multiplying by 2 to the um on first the left and then on the right then shows that we do indeed have that commutation between the um and its conjugate transpose, so we've proved the normality. And then so for every m, the am has determinants either 2qm to the 2m minus 1 or this. And then 2 am inverse is given by this formula, where dm is exactly what we had before, and the trace and determinant are what they obviously should be. This comes from taking real absolute values. And then since am is the matrix, I should say that this is the absolute value of this, not the full thing. And then since we just use the fact that am is dm um, and then apply dagger, and we're done, because all the identities fall from what we did above. So our next result then summarizes everything we've done, and it tells us exactly how we can solve the FAR equation. Let m and n be positive integers, with n less than or equal to m times 2 to the m minus 1. And let t be a translation operator over the two adics with coefficients in the cyclotomic field QQ 2 to the nth root of unity, and suppose that t has ceiling 2 to the m. Then t is a non-trivial FAR identity approximating translation of fqx hat of tolerance q to the n if and only if the following hold. The q-adic supremum norm of CT is strictly greater than q to the negative n, meaning that this guy has at least one entry whose q-adic absolute value is strictly greater than q to the negative n, and that CT is equal to q to the n over 2 to the m times um dagger times dm inverse times u, where u is some 2 to the m by 1 column vector in this cyclotomic integer ring. So proof. First, let m, n, and t be as given, and suppose t is a non-trivial FIAT of given tolerance. Then by our lemma, we have that am CT is congruent to 0 mod q to the n. So that means there's some vector in this space such that this holds. Since we know what the inverse of am is, we can then compute it and say that CT must be all of this. Since v is in this thing, the vector u equals v over q to the n is in that thing, and we get this, which shows that t has the desired form. As for the magnitude estimate, also non-trivial, it's important. It's also for the magnitude estimate on CT, since t is given to be non-trivial with tolerance q to the n, we have this, and here we get that because this is equal to 1 in absolute, in supremum norm. And finally, t is the norm of t is equal to the supremum norm of CT just by definition, and so that gives us our estimate. Next, suppose that CT's supremum norm is strictly greater than q to the negative n, and that it has this form. Then multiplying by am, we get this, and so we have that, which means that t is an FIAT of tolerance q to the n, and then non-triviality follows again by the fact that the supremum is 1. In summary, a solution, and so we're done. A solution to the FAR equation of tolerance q to the n is a translation operator of height 2 to the m, whose coefficient vector c satisfies AMC, q-adic absolute values of its entries, the maximum of that, is less than or equal to q to the negative n. The above two results show that the set of all coefficient vectors satisfying this property is precisely the image of this space under AM inverse. Having thus solved the FE, all that remains... Of course, this is much easier said than done. Our theorem shows that any non-trivial solution of the FE of ceiling 2 to the m and tolerance q to the negative n is going to have a coefficient vector in this set. And as we saw earlier, the non-triviality of T was required in order for T to be an identity approximating translation. That is, C being in this space is necessary for T to extend from a solution of the Farr equation to a solution of the full identity approximation problem. However, if we examine near values of T, that is, T's coefficients where the index is strictly less than the ceiling of T in absolute value, it turns out that confining CT to this space is not enough. In fact, to that end, there is an even stronger notion of non-triviality than the one that we've been currently using. Given a bounded, and this is as follows, given a bounded function chi hat with and epsilon be strictly between 0 and 1, let T be an FIAT of chi hat of tolerance epsilon. Then we say T is strongly non-trivial whenever T of chi hat of 0 minus 1 has a q-adic absolute value less than or equal to epsilon. As a result, the previous notion of non-triviality, this thing, I'm now going to refer to that as weak non-triviality. The importance of strong triviality comes from the observation that every identity approximating translation is necessarily strongly non-trivial. Of course, strong non-triviality implies weak non-triviality, as we'll prove. Suppose T is strongly non-trivial, and suppose by contradiction that T is somehow not weakly non-trivial. Then we have this should be a less than or equals. Then every coefficient of T has absolute value less than or equal to that. Go through our computation, and we get the same contradiction. Yeah, as in the case where all IATs have to be weakly non-trivial. With a strong non-triviality, we can then stipulate a refinement of our solution of the Farr equation, which begins to take into account the dependence on x. Let m and n be positive integers, let x be a non-zero integer, and suppose T is in its usual translation operator space and has height 2 to the m, and it is an IAT, tolerance q to the n. Then we have our mn relation. C is in the space that solves the Farr equation, and we also have to have this not strongly non-trivial condition here, and in particular, this thing has to have a q-adic absolute value of exactly 1. And the proof, this is just immediate from what we just said up there. And let's see, because any T whose coefficient vector is in the image of that, under that will solve the FIAP of tolerance q to the n, we get a great deal of variety in the possible values for the q-adic norm of such a T. Moreover, for any fixed choice of V, the norm of T will increase when m is increased and decrease when n is increased. Now let's move to the near equation. As with the FE, we can set things up in terms of matrices. And here what we're doing is it's Rn of chi hat is equal to this, where the pattern keeps going. It's each column and row we're indexed by S and T, and in both cases we're using the denominator enumeration. And just for brevity, I'll write Rn to denote this one. Then the near equation can be written in matrix form, like so. For given m and n, and x and t, and then we have a near equation solution of tolerance q to the negative n, if and only if Rm minus x times a 2m by 2m identity matrix sends Ct to within q to the n, to mod q to the n to E0, where E0 is a 2 to the m by 1 column vector whose topmost entry is 1 and whose every other entry is 0, and the proof is just by writing everything out. And then with this disposal, we can summarize our work as follows. Let m and n be blah, 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 and then we have that an identity approximating translation T is a tolerance QN that this holds if and only if all of these things happen. So this is the condition relating the height to the tolerance, the ceiling to the tolerance. This is saying that CT is a non-trivial solution of the far equation, and then here we have the solution of the near equation. Yeah, so obviously the difficulty in solving the full IAT comes with dealing with the near equation. Using 2, we can in fact write 3 as this. And so then this here, if such a U exists, then there's an IAT, and then we get our this is just a restatement of this theorem in terms of spans and translates. So before we conclude, there are 2 points worth addressing. The first has to do with Rm, and a brief examination reveals that Rm isn't just a random matrix, but is in fact a circular matrix. And these are matrices which look like this. And the reason why they're important is because they are fundamental to finite Fourier transforms. Given a circular matrix, we call its associated polynomial is this guy. And then Rn of chi hat is going to be, as defined, it's going to be a circular matrix for all chi hats. And then the fundamental property is that the circulant is that when we consider the circulant matrix Rn of chi hat, the associated polynomial is the one whose coefficients are the values of chi hat on a neighborhood of 0 in z2 hat of radius 2 to the n. And so again, with this, we then get a very nice description of their eigenvalues and stuff. Namely, the determinant of a circulant matrix is the product of its associated polynomial evaluated at omega to the n, product from n equals 0 to n minus 1, where a is n by n and omega is any primitive nth root of unity, and then these are the eigenvalues. And so with this, we then have that the eigenvalues of Rn of chi hat minus lambda is going to be equal to precisely the values attained by the nth resummation of the Fourier series generated by chi hat. And the proof is just a computation. Yeah, and so this actually I have a conjecture. I'm pretty sure this is true, but I might be a little bit too lazy to prove it. For any prime number q and any integer m greater than or equal to 0, Rm, that is Rm of chi q hat, is going to have all non-integer rational eigenvalues. Finally, when dealing with the near equation, it may be of interest to examine things from a Galois theoretic perspective. And for any t, note that this thing is going to be a polynomial in e to the 2 pi I t with rational coefficients. So if we pick a field extension k of qq and confine t to there, observe that for near t, this thing here is a polynomial px t xc, where xc denotes e to the 2 pi I over ceiling of t. And consequently, the task of computing this q-adic absolute value is the same thing as computing the q-adic absolute value of this trigonometric polynomial. So then the idea here is, well, let's look at the splitting field of the trigonometric polynomial, which then we get a factorization like this. And then if we consider the Galois closure of the splitting field, we then have that its q-adic absolute value comes directly from the field norm. And so we have that the q-adic absolute value of px t of xc is equal to the product of the q-adic absolute values of xc minus the roots in the Galois closure of the splitting field. Of particular interest is the condition where we could treat, instead of treating the unknowns here as the coefficients of t, rather we choose the roots of this polynomial as our unknowns. And so pick roots so that the coefficients behave well. And that in particular, we want to choose roots so that these absolute values are easy to compute, and then use Vieta's formulas to express the CTs, the coefficients, in terms of the chosen roots. And this would involve studying towers of the form Q to field where our translation operator takes its coefficients, cyclotomic extension, Q to closure, then this adjoining the cyclotomic extension, then the Galois closure. And as an example, and also here's where we get some interesting dynamics for when Q equals 3 versus everything else. When Q equals 3, the only roots of unity in the 3-adic integers are 1 and negative 1. In other words, every cyclotomic extension of the rationals, none of them except Q itself, can be embedded in Q3. And because of this, we don't need to worry about how the embeddings affect the values of roots of unity when computing the absolute values. And in particular, we then have that for any 2-power root of unity C, the Galois group of Q3 of C over Q3 is the same thing as the Galois group of Q of C over Q, which is just going to be then isomorphic in the standard way to the group of units of Z mod 2 to the mz, where 2 to the m is the ceiling of our translation operator, and so blah, 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 blah. If we make the requirements, an example, suppose we choose our P so that its roots are all 3 Adic rational numbers. Then when we go through the computation, we end up getting that the 3 Adic absolute value of our polynomial is the product of the 3 Adic absolute values with roots of the ceiling of teeth cyclotomic polynomial evaluated at the roots. This cyclotomic polynomial is this particular form. In order for this to be less than or equal to epsilon, say less than or equal to 3 to the negative n, we need for this to occur. And in order for this to occur, we need for r to the ceiling of t over 2 to be congruent mod 3 to negative 1. Since if we choose t to have a ceiling of at least 4, this then means that we can reduce this to that condition that a squared is congruent to negative 1 mod 3 for some a, but this is impossible because negative 1 is not a quadratic residue mod 3. Hence, for any choice of roots in Q3, coefficients in Q3, which solves our near equation to tolerance epsilon less than 1, such that our polynomials also have roots in Q3. And then finally, as I said, the other thing we want to explore is when we move away from just looking at the Q-adic, or in this case, 3-adic absolute values, but instead approach things using the product formula, and whether or not that might be of interest. Next time, we're going to be looking at what I consider personally is the most exciting part of all this, which is that we're going to talk about the powers of chi-q. That is, chi-q the value squared, chi-q the value cubed. Things get really interesting there. See you then.